All right, y'all. Today we're going to be talking about Pythagorean theorem and the distance formula. Both of these are things you're probably familiar with from before, but we're just going to go over a quick refresh to make sure we're all on the same page. But before we start that, I want to see how much you remember from last class with our simplifying radicals. So go ahead and pause the video and do our simplifying radicals warm up on numbers 1 through 8 for me. Are y'all checking in and making sure we all got the same answers on our simplifying radicals warm up? Number 1 should be 3 square roots of 3. Number 2, 2 square roots of 7. Number 3, just 3. Number 4 is a little tricky. We get the root 11, which gives 11. 3 times 3 is 9, which then gives us 9 times 11, which is 99. And 5 and 6, relatively straightforward. 5 is 7 square root of 5. Is that missing number of 7 to make 11 square roots of 3. And then 7 and 8 are those split radicals because of the division. So we can't simplify the top, the numerator, but we can root that denominator on both of those. All right, now that we're all good on our radicals, because we're going to be using them today, let's talk about the Pythagorean theorem. So the Pythagorean theorem has to do with right triangles, and specifically the sides of right triangles. So our right triangles are any triangles with that 90-degree angle, and those sides of our right triangle are called the legs. And side C, that longest side of our right triangle, is called our hypotenuse. And the Pythagorean theorem is used to find that missing side length on a right triangle. So we can only use it on right triangles. We cannot use it on just any triangle. And of course, that formula for our Pythagorean theorem is a squared plus b squared is equal to c squared. That should be familiar, hopefully. Okay, so let's do a couple of we do's real quick, and I'm going to let you try those you do's. So we want to find the missing side. So we have 7 and 8 as our two legs, and x as our hypotenuse, which we don't know. I like to sometimes label the sides just so I know which one is which. So we have A and B, but we are looking for that C. And remember, the way I know that these are legs is because they are the sides with our right angle. The hypotenuse is always that side that is across from the right angle. So let's go ahead and set this up. If I want to solve for C or for X, I'm going to plug 8 and 7 into my Pythagorean theorem. So 7 squared plus 8 squared is equal to c squared. Okay, and then I can simplify from there. 7 squared is 49 plus 8 squared, which is 64, would give me c squared. Okay, and then I can add these together. So that would give me 40 and 60 is 100. 9 and 4 is 113. So 113 is equal to c squared. All right, and then last but not least, I want to square root both sides to get that c by itself. So square root of 113, square root of c squared. We get c is equal to the square root of 113. Now, I do always want to check to see if I can simplify that radical or that square root in any way, just like we've been doing. So we want to check, is 113 a number that we can actually simplify? And the way to do that is just to think of those factors. So is it divisible by 2? Is it divisible by 3? Is it divisible by 4? To try and get those perfect square factors that we've gotten before. But try as we might, we're not going to be able to find anything with 113 because 113 is actually a prime number. So that is as simple as we can get it, that square root of 113. Now, if I wanted to, I could use a calculator to find the exact side length of x. But if we don't have a calculator, we just have to leave it in terms of that radical. Okay, let's do one more together. So find the missing side, given 6 centimeters, 13 centimeters, and then our side x. So let's label our sides real quick. So A, B, and C. And one quick note I want to make, it does not matter which leg is A and which leg is B. They are interchangeable in the formula. Okay, so we can see this time, instead of our hypotenuse being our missing side, one of our legs is our missing side. So let's go and set this up in our formula. So 6 squared plus b squared is equal to 13 squared. And then just like before, we can square out everything that we can. So 36 plus b squared is equal to 13 squared is 169. And then from here, this time I got to get b squared by itself first. So I can subtract 36 from both sides. And that gives me b squared is equal to 133. Square root both sides. And we get b is equal to the square root of 133. Now, just like last time, we of course want to check, can I take the square root of 133 any further? Looking for those factors. Is it divisible by 2? Is it divisible by 3, 4, 5, 6? And in this case, it is divisible by a smaller factor. 7 times 19, in fact, is 133. But that's not really a very useful number for us in terms of us trying to find a perfect square. So once again, we cannot make this any smaller, so we would just leave it as 133 for that missing side length. Hey, y'all. Go ahead and try those you do. Try those two over on the right side. See if you can do them by yourself. Pause the video, and then you can check with my answers here in a second. All right, y'all. Checking in, see if we're getting the same thing. So on our first you do, we got side A is 24, side C is 25, but we're missing that side B. So we can set up again 24 squared plus B squared equals 25 squared. Now those are pretty big numbers, but don't be afraid to do some long multiplication if you need to. We get 576 for 24 squared, 625 for 25 squared. Subtracting those, we do get b squared equals 49. And then square rooting both sides, we do get b is equal to 7. So this one came out pretty nice. And then similar with our other you do, we did get a nice final answer, but we got some gross side lengths, the square root of 10 and the square root of 26. For our A and our B, we're missing that side C. But when we square that square root, that does cancel out. So 10 plus 26 equals c squared, gives us 36 equals c squared, square root both sides, and we get c is equal to 6. I also noted that we could denote these answers as the actual side. So AD was the missing side in our first one, so we could say that AD equals 7. And then line segment LP was our missing side in our second one, so we can say LP equals 6. Either of those would be fine, and typically if it was on an assessment or something, I would make sure to denote specifically a spot for you to put your answer, just so we don't get confused. All right, now let's see if we can apply this Pythagorean theorem maybe in something a little bit different. So I want you to try this section over here on the left. So we're going to use the coordinate plane to determine the distance between the points A, which is at -2, -1, and B, which is at point 1, 3. Okay, now remember, those are x, y points. And now that we're plotting them on the coordinate plane, we do have to follow our cardinal directions. So our x's go positively to the right and negatively to the left, and y's positively up and negatively down. So go ahead and follow all the pieces for this. Try this and see if you can find that length of our actual segment. Okay, so go ahead and pause the video and do the try this. All right, y'all, checking in on our try this. So hopefully you plotted the points A and B and drew that line segment AB between them. Then drawing our horizontal line segment AC, we can see it right there horizontally, and our vertical alignment segment BC. We have the right triangle ABC with a right angle at our vertex. And we can note the coordinate of C is 1, -1. And our length of AC, we moved over 1, 2, 3 units, so it would be 3. And our length of BC, we moved up 1, 2, 3, 4 units, which would give us a length of 4. Plugging that into our Pythagorean theorem, 3 squared plus 4 squared would equal the length of AB squared. So 9 plus 16 would equal 25. Square rooting that, we would get 5 is equal to the length of line segment AB. So even though we have that single line segment, we can kind of build out a little triangle or build out that Pythagorean theorem to find the length of any line segment. So same thing we can apply on F. We have another line segment with legs 4 and 5 underneath it. So 4 squared plus 5 squared would give us 41, and then square rooting both sides, we'd get C is equal to 41, which is a prime number. So we would just leave it like that. Okay. So hopefully you kind of saw a more application piece of the Pythagorean theorem, and why this is important is because now we're going to use this to derive what we call the distance formula. The distance formula can be used to find the distance between any 2 points on a graph. Okay, so when we're trying to find that distance formula, we're going to use d for our distance, and the distance formula comes from our Pythagorean theorem. If you noticed, on both of our try thises, we had the 2 legs, and then we had to square root it at the end. So we had the 2 legs, and then we had to square root it at the end. So our distance formula is essentially finding any line and treating it as a hypotenuse. And anytime you have to solve for the hypotenuse, you always have to take the square root of that c squared to get it by itself. So we're going to take the square root of our, what would be our d squared, and then over on our right side of our equation, we have 2 different pieces. We have a spot that needs to represent A, that first leg, and our spot that represents B, our second leg. And you'll notice it says it wants us to do this from the point x1, y1 and the point x2, y2. And if you notice on our graph, we moved from x to x from A to B, and from y to y from A to B. So that's essentially what we're just doing, is we're doing the same thing we did graphically, but we're trying to make an equation out of it. So this x distance would always be represented by x2 minus x1. It's that distance I traveled from my first point to my second point. My y distance would always be y2 minus y1. That distance traveled in the y direction. And then these are going to give me those lengths of that kind of Pythagorean theorem triangle that I'm building. So I still need to square both of these. And that's really all there is to it, y'all, for the distance formula. It's just the Pythagorean theorem, but in some ways made a little bit more complicated, but it means the exact same thing. We're finding those 2 side lengths, squaring them, adding them together, and then taking a square root to be able to find the distance between those 2 points. So I know it says you do, but we're going to do one together, and I'm going to let you find the distance with our last 3. So we want to find the distance between CB, which that should be CB, not CD. So we'll just make a little revision right here that this is CB. Given the point C negative 4 comma 1 and the point B 3 comma negative 1. So just so we are all on the same page, C we're going to treat as our x1 and y1, and B we're going to treat as our x2 and y2. And then we can go ahead and set up our distance formula. So the distance is equal to the square root of 3 minus negative 4 squared plus negative 1 minus 1 squared. Now, a few important things to note. This negative and a negative are going to cancel out and make a positive. So 3 plus 4 would give us 7. And then negative 1 and negative 1 would give us negative 2. Now, another important thing to note when we're squaring it, obviously our 7 squared is going to give us 49. Our negative 2 squared is not going to give us negative 4, because negative 2 times negative 2 is still equal to positive 4. And then 49 plus 4 would give us 53. So our distance is equal to the square root of 53. Now, as always, y'all, we want to check, can we make 53 any simpler? Can we get it smaller? Do we have factors? See if we can get a little bit smaller down there. I believe it's prime, but it is always good to check. And indeed, 53 is a prime number. So we are all good to go on this one. That is as simplified as the distance without a calculator as we'd be able to get. So go ahead, y'all, and do these other 3 questions using that distance formula. You can also, if I give it to you graphically, if you want to do a graphical distance formula instead of using the points, you can do that as well, whichever one works best for you. So go ahead and pause the video, and then I'll go over these last 3 once we're done. All right, y'all, and once again, checking in on our U-dos. So on our finding of EF, we get negative 7 minus 11 squared plus negative 2 minus 3 squared. When we plug it in, we get negative 18 and negative 5. Squaring both of those, we get 324 and 25, which gives us the square root of 349. And 349 is a big one, but 349 is a prime number, so we would leave it just like that. And then on our bottom 2, I decided to kind of show you 2 different ways. So one way, I did our kind of shortened version of the distance formula because if I already know the change in x and the change in y, I can just plug those straight in. So looking at our triangle, we moved to the right by 3 and down by 6. So I went ahead and plugged in 3 squared and negative 6 squared for our change in x and change of y, which gave us 9 and 36, which gives us the square root of 45, which we can split into. I know we haven't done a lot of these with these notes, but we can split it into 9 and 5, which would give us a distance of 3 square roots of 5. And then our very last one, I went back and did the traditional one. Sometimes it's easiest to find the actual points, so negative 4, negative 1, and 0, 4. Then plugging them in, 0 minus negative 4 and 4 minus negative 1. Both of those are double negatives, which gives us a positive. So we get 4 squared and 5 squared, which gives us 16 and 25, which gives us the same square root of 41 we got earlier today. All right, y'all. That's really all there is to our Pythagorean theorem notes. I hope this kind of clears things up, and go ahead and work on some of the practice.